Hi everyone. Today's speaker is Cora Uhlemann, who is a lecturer at Newcastle University in UK. She received her PhD in 2015 in Munich, and after that she held 2 postdoc positions, one in Utrecht University in the Netherlands and another one in Cambridge, UK, before moving to her current position in Newcastle. She is an expert in theory and statistics of the large-scale structure, and she said she will be happy to be interrupted during the talk if you have any questions. And today she's gonna tell us about cosmology and fundamental physics with one-point statistics.
Great. Thank you, Elena, for the super nice introduction. Actually, today I tried to remember when's the last time I was in Waterloo, and I think I actually visited when I finished up my PhD in 2015. So obviously I would have liked to actually come by in person and see you all and actually chat with you over coffee. But well, I'm still glad to be invited for the remote seminar here. So thanks a lot for having me. And I also want to say hi, and I brought along my PhD student, Alex Guff. They started their PhD at end of September with me, and is going to push forward this kind of idea of probing cosmology and fundamental physics with one-point statistics. So today I want to give you a brief overview of why we care about one-point statistics and what we can learn from it using well, those kind of statistics to probe cosmology and fundamental physics. And maybe first, since lots of you might not have seen where Newcastle is before, so here's a map of the UK and the cosmology landscape. And Newcastle is the red spot that is close to Durham. I'm actually not sure whether you can see my cursor. Hopefully you can. So Newcastle is in the north of England, very close to the border of Scotland. And here we have a research group on the one hand for like theoretical cosmology and quantum gravity, but recently also building up some observational astronomy group. So you can find our web pages there and have a look on who's here. And today we are joined by my PhD student, Alex. So what is this talk going to be about? Essentially, the big story I want to talk about today is in the good old days when cosmology was mostly about the cosmic microwave background, things were very simple because essentially speaking, the cosmic microwave background is one snapshot, essentially from one rather early time, where everything was simple because matter hadn't clustered significantly yet and was in the linear regime. And at those early days that we can map through the cosmic microwave background, we can actually describe the matter distribution by extremely simple statistics. So at those early times, the statistics are almost Gaussian. And what that means is I can basically capture the full information just using two-point statistics. And I'm sure you have seen before, basically the power spectrum from the cosmic microwave background. Those are essentially the kind of two-point statistics that essentially characterize the whole matter density field at early times. And the cosmic microwave background is of course invaluable to actually determine cosmological parameters and learn key things about our universe. In particular, the cosmic microwave background is one reason why we are rather certain that there must be some kind of dark matter out there. And an additional hint was provided that the universe is actually in a stage of accelerated expansion. But the good old days, well, is not anymore. And these days we are in a more complicated but also more exciting stage. And we can actually set out to map the cosmic large-scale structure that I abbreviated as LSS here. So that's the cosmic large-scale structure. And in contrast to the cosmic microwave background, it's not really just one snapshot, but essentially a motion picture, because we can record galaxies at different redshifts and essentially record a video of our universe, how it forms structure over time. And the challenging bit is because of gravitational interaction that actually formed those very structures we can see today, the galaxies, the whole process there is actually non-linear. And this means the statistics we will need to use have to be non-Gaussian. Because even if you start from an almost Gaussian matter distribution, if you have nonlinear gravitational interaction, basically matter clumping, you will cause a non-Gaussian final matter distribution. And one reason why I'm particularly excited by this is that we can actually map the large-scale structure with state-of-the-art surveys. So the video you see here is actually made by the Sloan Digital Sky Survey, SDSS. And basically what they have been doing, they mapped the position of galaxies and their properties, even their like rough shapes and inclinations. And this is what you can see in this video. And now we have a huge set of new galaxy surveys lined up. And in particular, the Euclid satellite will map out the large-scale structure to higher redshifts and even more accuracy, mapping billions of galaxies to learn about our universe on large scales. So now the question is, what kind of statistics are actually useful to basically capture key properties of this distribution of matter, or more precisely, what we observe through the galaxy survey, the distribution of galaxies. So as I mentioned before, we have a couple of traditional statistics. And one of the key statistics is the so-called two-point correlation function. And the important bit is to realize if you have a Gaussian distribution, so a Gaussian matter field, like for example it was at early times, then it's fully characterized by this two-point correlation. So what is this two-point correlation? Essentially what you do, you make your map and you first compute the mean density at a given time. And this mean density is now your reference, and at every single point, you now describe with delta the deviation from this mean density. So essentially, you take your density, you divide by the mean, and now you say, okay, I have always 1. So if you get a 1, you will be at the mean density, but you could find a slightly larger value. Then you would say this delta that I wrote here is positive, but you could also be at a point where there's slightly less density than the mean density, then this delta would be negative. So this delta we call the density contrast. It basically compares the local density at this point that I called x here, compared to the mean density. And now what you do, you basically correlate the density at one point x with the density at another point at separation r. And I indicated this in my little plot here. So here you basically see galaxies recorded across different redshifts. And you basically fix the redshift you are at. So you look at this kind of redshift slice, and now you take out pairs of galaxies that are at a given separation from each other, that is R. And the interesting bit is, so this correlation function, because of statistical isotropy, it's only a function of the absolute value of R. So basically means it doesn't really depend on the direction, just on the absolute separation between those two points. Basically the separation of two galaxies. And essentially what this two-point correlation tells you is at what kind of separations from each other do galaxies like to cluster. So for example, if you're at very small separations, it's very likely if you already found a galaxy at one point that you will find a second galaxy at separation r from it if this r is rather small. If on the other hand, you are at very large separations, basically just because you know you have one galaxy at this point, you don't know much about the number of galaxies very far away from this point. So now the crucial bit is, if you have a Gaussian field, this two-point correlation basically encodes all of the information and tells you everything about the field. But now in the formula I wrote, you can already see if you have something that is non-linear, this will also mean the statistics are non-Gaussian. And there's a very simple reason to see that. So let's think about this density here. So I told you that gravitational collapse works in a non-linear way. And essentially what it means is that the final density contrast I find depends in a non-linear way on the initial density contrast. So you could think about that this delta I wrote here is, for example, some term that is quadratic in the initial density. So then you will plug in the square here, and obviously you will see what I wrote down there has then 3 deltas. That actually means it's not a standard two-point correlation anymore, but has some kind of higher order correlations. So now the tricky bit is once you have nonlinear interactions, your field is no longer characterized by just 2-point correlation functions. And the issue is now you need a whole hierarchy of new correlation functions to actually properly characterize the field. So for example, you could compute higher endpoint correlation functions. So for example, look at a 3-point correlation function where you now ask, what is the probability of finding a set of 3 galaxies arranged in this triangle, where you can now basically specify separations and angles that tell you the triangle configuration. And you could keep repeating this, going to 4, 5, 6-point correlations. And the issue is twofold. On the one hand, it's actually hard to measure this in the data because you can already see, while the 2-point correlation only depends on the absolute separation of the galaxies, the 3-point correlation already depends on separations and angles. And the more points you add, the more complicated to actually extract this. And it's not only about how accurately you can actually measure this or how straightforwardly, but also how well you can predict this from theoretical arguments. And it turns out to be actually pretty tricky to predict higher order endpoint correlations. This is why you can set out and ask, are there maybe different, simpler kind of statistics that still capture some of this non-Gaussian information that we would lose if we only looked at 2-point correlations? And the answer is that there are. And one particularly simple idea is the following. So you look at your distribution, and now what you can do, you can just look at a given volume. So here I just drew little circles, and you can just count how many objects you have in those little circles that I drew. And now you can look at the statistics of how many counts of galaxies you find in those cells. And now for every circle you draw, you will record one number, and now you can plot a histogram of this distribution. And this is a very simple example. It's actually a 1-point statistics, because essentially you forget about the location of the little circles I drew here. You just record the value in every single of the circles and then make a histogram. And it turns out that this 1-point statistics that we call the probability distribution function of basically the counts in those cells already recaptures some of the non-Gaussian information that you would lose if you would just look at 2-point statistics. So now I will make my life a bit simpler, since I'm by training a theoretical physicist, and now forget that they're actually galaxies, and first talk about dark matter, and basically asking how would the statistics of counts in cells look like if we could directly observe dark matter. So in this first simple example, what I can do, I can run a dark matter only n-body simulation, and I will get a nice box out of it that basically tells me how many dark matter particles are in different regions. And now what I did, I basically took a slice of my simulation and I draw little spheres. So basically I make my whole box, I put lots of little spheres in there, and then I just measure what is the density in all of those spheres that I drew. And now, as before, I want to normalize by the mean density. So basically I want to record spheres that are exactly at the mean density. I will say that they have density 1. Then spheres that are twice as dense, then I would say the density is 2 here. And for example, I could also have half of the mean density. Then I would say 0.5. So essentially what I do, I just make a histogram of all of those densities in the spheres. And you can see an example here of this histogram distribution that I drew from the simulation. And as you can see by eye already, this distribution is not a Gaussian distribution. In fact, it basically is skewed because the peak is actually at under densities. So it seems that most of the spheres are slightly below mean density. And then you have a very large number of spheres that have high density, so a strong tail here. While on the other hand, if you look for under densities, it basically drops very quickly towards 0 here. And just to guide your eye, I also showed a Gaussian distribution with the same variance. So essentially the variance tells you how wide this probability distribution function is. And obviously the black line and the black histogram look very different from each other. And what this tells you is that there is additional information in this 1-point probability of finding a certain density in the cell compared to just 2-point statistics that basically would be the square of the densities that gives you the variance. And the key idea is that we can actually use this additional information to learn about cosmology and fundamental physics. So before I continue, if anyone has a question on the basic bit, then please go forward now before I continue. Scrolling through the list.
Are you going to comment on the size of the cells? Because this histogram will definitely depend on that.
Yes, that's an excellent question. So the size I chose here is about 10 megaparsec. And I will come to the question of what is a good size to look at a bit later on. Roughly speaking, what you want to look in a regime where this variance is still significantly smaller than 1. We call this the mildly nonlinear regime. And essentially the idea is in this regime, you still have a chance of actually analytically predicting those kind of statistics. So this is why you're not allowed to look on super small scales. Does it answer your question?
Yes, I'm a little, because yeah, it's a 1 point. For example, one way I would look at it with a 2-point, I mean, the way we can count, like make shells and count the number of galaxies on the shells, and then the size is like, gives us a sense of a 2-point correlation, but depending on the radius, right?
Yes, that's actually correct, but maybe ask me this at the end of my talk. So you're absolutely right. I could basically do counts in cells with slightly different radii and then look at shells and extract some kind of 2-point information. You're right with this. But for now, we make it simple. Basically, think about it. I have my density field from the simulation. I smooth, right? According to the scale I picked for my spheres. And then I basically forget the distribution that was there initially. So in that sense, I call it 1-point statistics, because at every point, then I have the smooth density, right? And I forget basically the spatial arrangement. I just stack all of the densities and make the histogram.
Okay. Sounds good.
Thank you.
So it seems like there's a sort of basic linear prediction here, right? Because you're basically a fixed volume, but things are different densities. I mean, what does the linear prediction look like?
Right. I think that's a difficult question, what you would call a linear prediction. So I think the simplest linear prediction I would make is the following. We know that initially the distribution is close to Gaussian, right? So basically your initial density distribution would be Gaussian, and the linear prediction would be to say, well, all I basically change with linear growth is the value of this variance here, right? So essentially speaking, you can say that the variance just scales with the growth factor squared. So the linear prediction would be that this distribution is actually Gaussian and basically just changes the width over time.
Oh, I guess maybe that's not what I mean by linear. I was thinking, you know, if you just treat each cell as an isolated universe of fixed density, it's going to expand and the density will change at some rate, right?
Well, that's an excellent point, and that was actually what I was going to talk about next.
Okay.
So your intuition is right. We want to use spherical collapse to actually predict this. Okay, excellent.
That's where I was going.
Yes, so this was my next point. So basically the question is, just from the statistical point of view, we see now why we can extract information from the 1-point statistics. But this is not the whole story, because the whole question is, how well can we actually predict it? Because in the end, we want to predict a theoretical template for the shape of this, depending on cosmological parameters, compared to the data, and then find those parameters. So how can we predict those counts in cells? And the idea is actually very simple. Essentially, since I collected all of the spheres, so I chose one radius and then I just make a histogram, essentially what it means here, I have ideal spherical cows, just by the fact that I chose spherical cells. Considering the statistics of those spheres means essentially that I pick all of the spheres with the same mean density, no matter what is the density distribution in them. So basically those all have the same mean density, but you can see different spatial distributions. And the key idea is now, if you stack all of them, just because of statistical isotropy, you know that the stacked profile will be actually spherical. essentially due to the symmetry that we put in. And this is now an interesting observation, because now you can say, aha, if I have a spherical profile here, I can actually use spherical collapse to predict the shape of this probability distribution given the initial conditions. And to make this a bit more precise in how to do this, we use a very nice mathematical framework of so-called large deviation statistics. And the idea is extremely simple behind this. Essentially, we know the initial distribution is close to Gaussian, which basically means that it's exponentially unlikely to find very high linear densities, right? So essentially, you have a Gaussian distribution that is symmetric around the mean. So here I plot everything in terms of how big is the linear density compared to the kind of linear variance, or well, linear standard deviation here. So you are exponentially unlikely to find large deviations from the mean density here. So let's just forget the prefactor. And now the interesting thing is we already know how this initial density distribution depends on the linear density contrast. And now the question is, how can we map this to the final density contrast? And we can actually do this by using spherical collapse. And the key idea is, if you use spherically symmetric configurations, so my spherical cells, you can essentially plug in spherical collapse there and get your final distribution by essentially using spherical collapse to map the final density rho. So this includes now the mean, so it's basically 1 plus delta nonlinear. You can relate the final density to the linear one using spherical collapse. And now the additional thing you need to take into account is that, as was mentioned before, actually radii change because you have mass conservation. So essentially spheres will change their radius according to the density you find. So the key thing is we take essentially the initial conditions and we can use spherical collapse to predict the final shape of this probability distribution. So in some sense, the idea is the most likely path of the evolution dominates here. And this most likely evolution is the spherical collapse. And you can already see how cosmology enters here because I have the linear variance that depends on the redshift that I'm looking at. So for example, sensitive to the growth of structure. It has a scale dependence here. So depending on which density I look at, I probe different scales. And obviously, in principle, we also need the nonlinear variance here. So in some sense, this is just a simple rescaling to make the nonlinear variance correct, basically match the correct width of the PDF. And in some sense, you could see the nonlinear variance as some kind of external input. Either you measure it in data or the simulation, or you use some kind of prescription for the 2-point statistics to predict this nonlinear variance. So now, how does this spherical collapse work? As was mentioned before, due to mass conservation, so initially densities are basically very close to 1. So essentially, initially, the mass in a given sphere is just determined by the radius, the initial radius that I call little r here. Well, now, since the overall mass is conserved, if I find a large density rho, this means the sphere actually needs to contract. So the initial radius will be larger than the final radius. So essentially large densities contract, while on the other hand, if I look at an underdensity, they seem to expand. So the important thing is if I fix the final radius, by looking at different densities, I essentially probe different scales in the initial conditions. So this is the first ingredient. Mass conservation tells us how to relate initial radii to final radii. And the second ingredient we now need is to relate linear densities, delta L, or density contrasts, to the nonlinear densities rho here. And you can essentially write down a differential equation and solve it. And it turns out to be particularly simple if you are, for example, in a pure Einstein de Sitter universe, where you can basically write down the spherical collapse solution. And you can find an even simpler approximation that is just a power law that I stated here, that basically relates the nonlinear density rho to the linear density delta L. And I made a little plot here. So if you had linear evolution, then the density would be just 1 plus the density contrast. So this is the dashed line. And what this density mapping from spherical collapse essentially tells you is that if you have large linear densities, then nonlinear collapse basically increases this compared to the linear prediction, which I guess is not very surprising. While for underdensities, basically it's also nonlinear, but actually a lot smaller than the linear prediction. In particular, you cannot go below zero final density. So using those very simple ingredients, we can now predict this distribution of matter counts in cells from first principles. And here I show you a comparison to state-of-the-art simulations from the Quixote simulation suite. For example, Elena was very involved in this simulation suite here. And what you can see now, I have solid lines that are the theoretical predictions using spherical collapse and the initial conditions that I showed you before. I have data points that are measured from the simulation, and they have error bars here, so that's why they might be hard to see. And I show this for one chosen scale, so the radius of my sphere is 10 megaparsec over h, and what I change here is redshift. So if you look at higher redshift, around 3, you can see that your distribution doesn't look too non-Gaussian. I mean, still, it's not quite symmetric around the mean density, and you can see it actually already has some kind of overdense tail here. But if you now go to lower and lower redshift, gravitational collapse progresses and basically makes this distribution more and more non-Gaussian if you go to redshift 0 here. And the other important bit would be, what are the dashed lines that I'm showing here? I'm pretty sure a lot of you have heard of the so-called log normal model, where you essentially assume that this distribution is not a Gaussian, but basically a log normal, meaning that the logarithm is a Gaussian distribution. And this is shown as dashed lines here, just highlighting that this kind of phenomenological model is decent, in particular if you look at higher redshifts. But if you actually have a modeling from first principles using physical inputs like the spherical collapse, you can do a far better job at actually predicting this shape of the probability distribution. So now this is exciting. Now that we essentially validated our model, we can now use it to ask, how does the shape of this probability distribution change if we change cosmological parameters? So first I want to show a couple of plots here. So first, let's change the matter content. So for example, if I change sigma 8, roughly speaking, sigma 8 translates into the nonlinear variance. So if I have a larger sigma 8, I will basically increase my variance. And if I have a smaller one, I will decrease this. So roughly speaking, the width is determined by sigma 8. So what happens now if I actually change the matter density, omega m here? Well, what happens, there are two things. On the one hand, you change the growth. So if you basically compare the different plots at different redshifts, you could detect a change in omega matter. But additionally, you can also detect it in the kind of way in which this curve is skewed here. And a crucial bit, and I will show this later in more detail, is that the width determined by sigma 8 is not fully degenerate with the change you have when you change the omega matter parameter. So that means with the full shape of the PDF, you can actually disentangle the two. Sorry. So let me continue. What about other cosmological parameters? For example, you could ask, how sensitive is this to the dark energy equation of state? Well, now clearly dark energy determines the growth, which now means you can read off the shape of the PDF whether you have more expansion than a cosmological constant or slightly less expansion. And again, the story is here. You can look at different redshifts to even better disentangle the two, and they're not fully degenerate with the other parameter, sigma 8, that just determines the overall width, and omega matter that kind of tells you how skewed this distribution is. Finally, what I find particularly exciting is that essentially what we are able to probe here is different density environments. So for example, this statistics is also sensitive to massive neutrinos. Essentially what happens if you are in underdense regions, neutrinos constitute some kind of partially clustering background. And you can see this here if I compare the distribution for massless neutrinos the solid line to the one with massive neutrinos, you can see a clear difference in the underdense tail here. And this essentially comes from the fact that the overall matter density is a combination of cold dark matter and baryons and the neutrinos. And essentially the neutrinos that don't cluster or don't cluster as much as the dark matter basically change the results here. And you cannot only see this in the deep tail here, where the densities are very low, but also close to the peak. That is just hard to see here because I've chosen a logarithmic scale in this case. So this is important. We can actually see how the shape of this matter PDF changes with changing cosmological parameters. So we can now actually probe cosmology and fundamental physics with that. And one way we wanted to convince us that this actually works is using simulations. The key idea is here we want to validate our theoretical model, checking that it actually correctly predicts the response of the shape of this matter PDF with respect to cosmological parameters, and then make a forecast on how well you could constrain different cosmological parameters. And let me quickly advertise the Quixote simulations, which are in some sense ideally suited to perform a simple Fisher analysis that allows you to estimate how good you can do in terms of constraints on cosmological parameters. So for example, there are 15,000 realizations at the fiducial cosmology, so basically your reference model, and then 500 simulations each, changing every single one of the cosmological parameters going in the simulation. So you separately change sigma 8, keeping all of the other parameters constant, then you go ahead and change the next parameter. And from this amazing suite of simulations, we extracted more than 1 million PDFs to essentially estimate how well you could constrain all of those parameters. And the tool we used here is the so-called Fisher matrix. And the key idea is, in order to predict how well you can constrain your parameters, you need essentially 3 ingredients. The first ingredient, you need to choose what are your summary statistics. So if people do 2-point correlation functions or power spectrum, this would be the choice here for the summary statistics. But in our case, we choose to look at different bins of this matter density PDF. So those are our chosen summary statistics. Now what you need to do, first you need to predict how those summary statistics actually change when you change cosmological parameters. And those are the so-called derivatives here, because you basically see how the summary statistics, so the PDF, change if you change different parameters. So this is the first part of the ingredient, but that's not enough. You also need to know how correlated are the different bins of the PDF with each other. And this is the information that goes into the so-called covariance here, or covariance matrix, that basically tells you correlations between different PDF bins and also how big the errors are when you measure the PDF. And with this kind of Fisher matrix, what you can do, you can invert it in the end and estimate your marginalized errors on every single parameter using this Fisher matrix. So essentially, this allows you to do a forecast for cosmological parameters. And now let me just show you one example here. This is a validation of our theoretical model, again, in terms of solid lines here, with the measurements in the simulation. And essentially what we do here, we compare 2 different probability distributions with changed parameter, in this case, sigma 8. You increase it slightly, you decrease it slightly, and you look at the difference. And we choose particular variables here to highlight if you change sigma 8, essentially what you change is the width of the PDF. So if I increase sigma 8, I make my PDF broader, which means the peak goes down. This is why you see the dip here. But then basically it's larger because you increase the width here. So the way those plots work, you can roughly tell that basically the integral over all of this should be 0. So if you decrease the peak, you basically have to increase the outskirts in the tail. An important bit to keep in mind, if you change the width of the PDF, you see this clear signature that is roughly symmetric around 0. And now if I look at different cosmological parameters like omega matter, you can see that the signature is clearly different from this. And this is what I talked about before. If you change omega matter, you also change the skewness of the PDF. So the way in which it looks different for underdensities and overdensities. And similarly for neutrinos, you will see a clear environment dependence. In particular for the neutrinos, it's very relevant for the underdense regions you can see here. And the key idea is if all of those signatures look different, you are able to disentangle all of those cosmological parameters. So let me continue. Here's an example of how the correlation between different PDF bins looks like. I think the important takeaway is this covariance matrix is not diagonal as it would be for like simple power spectra in the linear regime, because obviously density PDF bins are correlated. But I can go into details later if you are interested in how exactly this works. Let me now actually show you some results and a little primer here. I think what you should keep in mind, we usually consider the power spectrum as the kind of workhorse for cosmology, but the matter PDF is somewhat the underdog and still carries a lot of relevant cosmological information. In particular, I made a very simple plot here where I only allow two parameters to vary: the amplitude of structure, sigma 8, and the neutrino mass. And the crucial bit is if you only look at mildly nonlinear scales at the power spectrum, so I chose a cutoff scale here, actually the power spectrum has real difficulty disentangling those two cosmological parameters. On the other hand, the matter PDF can disentangle the two, essentially because neutrinos have a clear density dependence in their signal. And this is what the PDF picks up on, which is why I think it's really promising to actually combine 1-point statistics with 2-point statistics to increase constraints. So here's a full forecast for now 6 cosmological parameters. So essentially we have lambda CDM parameters plus neutrino mass here. And the important takeaway is not how exactly those contours look like, but if you compare the matter PDF, which is shown in green, to the power spectrum in blue, you can see that in lots of cases, actually they have different degeneracy directions, which means if you combine the two, you can break degeneracies and improve your constraints. And additionally, those kind of late-time probes are also complementary to what we learned from Planck cosmic microwave background measurements. So clearly we can gain something by complementing early with late-time observations and then using different statistics here. Okay, so a little wrap up for this first bit. We found powerful 1-point statistics that are non-Gaussian and can be predicted beyond perturbation theory. And we saw that they have very robust and accurate predictions. And we can actually probe cosmology and fundamental physics with it. So here I focused on standard cosmological parameters and neutrino mass, but you can also probe primordial non-Gaussianity, for example. Now, the last bit of my talk, I actually want to focus on a very important bit is, you might now say, this sounds kind of encouraging, but unfortunately, in reality, we cannot observe the 3D matter field directly. And there are 2 ways around this. So essentially, we need to look at real observables. The first opportunity is to look at weak gravitational lensing, with which we can predict the overall matter field, but only in a projected way. And this is what I will focus on for the rest of my talk, but let me just mention that in principle, you can also look at galaxy clustering, where you can probe a 3-dimensional field, but not the one of overall matter, but the ones of galaxies. So in order to do this, you would need to include galaxy bias and stochasticity. But for now, let's stay on the matter side and think about weak lensing. So how can we look at 1-point statistics for weak lensing? And I will simply call this lensing in cells, similarly to counts in cells. So what is weak lensing and how does it work? So very roughly speaking, weak lensing is the weak version of gravitational lensing, with which we can also see very strongly lensed system, where you can see multiple images, for example. And the rough idea is, let's consider a very simple source that is just circular, and a bunch of dark matter clouds that is between us, the observer, and the source. Now, Einstein told us the presence of matter basically curves space-time and hence deflects the light that is coming from the source. And this leads to the effect of weak gravitational lensing that basically slightly changes first of all, the size of the source that we are seeing. So it can, for example, appear slightly larger or slightly smaller. And this property we call the convergence. So the convergence tells us whether it's magnified or demagnified. And then it can also change the shape. And we parameterize this in terms of the so-called shear. So essentially, weak lensing can convert a circular source into something that's more or less elliptical and also can be either stretched or squashed. And the two observables we have here is the convergence, kappa, that basically tell you the size. So if the observed or apparent size is smaller than the original one, we say that this is a negative convergence, while if it appears larger, we say it's a positive convergence. And similarly, the shear basically tells us how the shape changes, and you can change it in basically two kinds of directions. So here you can like either elongate it along this direction or squash it, and then you can do the same in a kind of 45-degree change direction. And I will for now focus just on the convergence that basically just tells you about the size. And the important thing is we are in the regime of weak lensing, where basically the value of this convergence kappa and the shape parameterized by the shear is always much smaller than 1, meaning that those changes are actually very, very hard to observe. So very slight changes in shapes and sizes of sources we see. And now obviously what we do in weak lensing is we don't look at single sources, and they are not circular, but indeed we look at lots of galaxies. So the idea is you have a bunch of galaxies at a given source redshift, and those galaxies are now lensed by the dark matter structure that is between those galaxies in the background and us. And the important bit is that if you have galaxies in lots of places, you will be able to see different parts of the large scale structure, basically everything that is between the galaxies and us. And galaxy service like Euclid essentially can make maps of galaxy shapes. And if there is dark matter in front, those galaxy shapes will be distorted compared to what they would look like without the lensing. So if you had very simple galaxy shapes, they would all be the same shape and completely aligned, then weak lensing would lead to this kind of crucial pattern here with which you can detect what kind of matter is between the galaxies in us. And the key bit is here, essentially we can record the galaxy's shapes, and from this we can reconstruct a two-dimensional map that tells us about all the matter between the galaxies and us. So now, how does it work in practice? So I'm interested in weak lensing in cells. So essentially, what I want to be able to predict is the statistics of a kind of cone where I have lots of matter in between. And now the question is, how can I predict this with the tools I introduced before? The simple idea is what weak lensing does is basically lots of matter in slices. So I can slice the cone in lots of circular slices. And lensing basically just modifies the way we add slices by adding this lensing weight in a way that it depends on the final source redshift. So that's where our sources are located. And then the redshift we are probing in between. And the key bit is here, you can predict densities in slices similarly as we could predict densities in spheres. But now, since the slices are two-dimensional, you have to use cylindrical columns. So I will skip this bit because essentially the idea is we can predict statistics of densities in disks with the same methods we use for spheres. And now we can integrate this up to get the weak lensing convergence from them. So let me skip to the slide with the crucial bit here. So the crucial bit is that the weak lensing convergence is built by lots of little density disks and weighted by this weak lensing weight here. And we know the functional form of this weak lensing weight. So now we are basically able to predict the statistics of this weak lensing convergence now we change the radius of the sphere is no longer, now we have an aperture, so basically an angle that tells us how big the cone is we are considering here. So theta is basically our new parameter, but we need to make sure that we don't look at too small scales. So now, how does it actually work? So we can predict the statistics, in particular the probability distribution for this weak lensing convergence as before. And let me show a plot here. So this is a plot now again in a logarithmic scale in a way that you can actually see the tails here. And a crucial bit is if you look at large enough scales, so here we look at 10 to 50 arc minutes, you can actually do a very good job in predicting the shape of this probability distribution. Let me actually zoom into the peak. So the peak is around kappa equals 0. And you can see that even here you can predict the shape of this PDF at a percent level accuracy here for different scales. And this is the key thing we can actually use. Let me skip the next bit. So this is the key thing we can use. We can now predict the shape of this lensing convergence probability distribution. And again, we can validate with simulations. So in this case, we have weak lensing maps generated from the dust strain pathfinder simulations. And we find that our theoretical formalism predicts the shape of this convergence PDF well. And you can also show residuals. Again, if you stay close to the peak, you have a percent level accuracy. And now you can essentially repeat the whole thing we had before. If you want to constrain cosmological parameters, you need to look at changes in the shape of this PDF when you change single parameters. And here's a little validation for this. So again, you can, for example, see if you change sigma 8, you clearly change the width of this lensing PDF. So you will, for example, if you increase sigma 8, you will lower the peak and widen the PDF, which is why this shape looks kind of characteristic here. And now, if you change other cosmological parameters, they lead to similar signatures. And in the end, the question is, can you actually disentangle different parameters? So in the case of lensing, it's a bit more complicated as for matter, because essentially you see that, for example, if you change the matter content, omega matter, you see a similar kind of signature compared to sigma 8. But you can also see clear differences. And in the end, what you have to do, you have to perform the full forecast to actually see how well you can do. So since I'm almost out of time, let me maybe show one of the key results here. So in this case, we have 3 cosmological parameters. In this case, omega matter, or more precisely, omega cold dark matter. We have sigma 8, the amplitude of structure, and in this case also W0 that basically parameterizes the presence of dark energy. And again, here we compare the PDF, in this case of the weak lensing convergence, combined at 2 different smoothing scales that are around 10 arc minutes each. And we compare it to the green curves, which are the lensing 2-point correlation function. So basically the 2-point correlation function of the weak lensing convergence in green. And you can see that there are slightly different degeneracy directions, which is promising because it means you can actually combine the 2 probes to gain more cosmological information. And finally, let me mention that this is not just done by us, but also part of a Euclid project, where we essentially look at a whole selection of higher order weak lensing statistics and basically ask the question, how much complementary information can we extract? And I think I'm out of time, so let me just wrap up here. So to summarize, 1-point statistics can be powerful. We can capture some of the non-Gaussian information of the matter field. We can make very robust and accurate predictions from first principles. And crucially, we can probe different density environments. And this essentially allows us to probe cosmological parameters and fundamental physics. So for example, massive neutrinos or primordial non-Gaussianity, with, in principle, the matter density PDF that we showed here as a kind of proof of concept. But of course, in the end, you need to go to observables. And I showed you one such example, namely looking at the weak lensing convergence PDF, where you probe the projected matter between the galaxies and us. And even in this case, we are able to show that you can extract cosmological parameters and basically enhance your constraints compared to just using 2-point statistics. So thanks a lot for your attention. I hope you will have some interesting questions for me.
Thank you, Cora. Are there questions?
I have a question. Hi, thanks for the nice talk. I had a question about, the practicality of these types of statistics in realistic data sets, because, I mean, it went by pretty fast, but some of these deviations look very subtle. And I wonder, there's not just shape noise, which we sort of understand. There's all sorts of other potential contaminants, whether they're, I don't know, cosmic rays or charge transfer or who knows what, that, might affect particularly the tails of the distribution. So I wonder if you have any comments on that.
Well, that's an excellent question. And that's why I maybe want to apologize for initially showing this logarithmic plot with the tails. So what we're actually doing in practice, we don't propose to actually use the tails. So what we typically do, we actually cut off the tails. And I think in this case, we cut off 2 and 5% in underdense and overdense regions. So we really just focus on the central region of the PDF to avoid lots of those kind of additional effects, in particular, even baryonic effects, right? We know that happen in very overdense regions. So this is the first bit. Shape noise is actually included in this kind of analysis. I think one of the challenging things is actually to deal with masks and stuff like this. So essentially for this analysis, the rough idea would be we need to rely on a convergence map, right? That is basically generated from shear observations, and you have to do mass inversion there. And I think actually masks, well, probably more of a limiting factor. So you need to be careful on how gaps in your initial shear map then propagate to your convergence map. So I think I would say lots of those effects like cosmic rays and whatever that are somewhat localized. I think my intuition would be that those effects are not too large because we smooth at rather large scales here. So it's like 10 arc minute scales. So I would hope lots of localized effects are not too important, but for example, masks are a clear thing to take into account. And this is one thing we're actually doing within the Euclid project.
Thanks.
Does it somewhat answer your question?
Yep.
Are there other questions?
So, hi, Cora.
Hi.
Hey, it's a very nice talk. I'm sorry, I don't have very interesting questions. I have a few boring questions. This question of whether a spherical collapse works, first of all, I mean, we know there are deviations from a spherical collapse. So, I mean, did you try to include them in some systematic way? You just said they're just too small for your purposes.
Well, I don't think that's a boring question at all. I think it's actually an extremely interesting question. So let me maybe go back. So you are absolutely right. Essentially what I used here is the following intuition. So when I write down this formula, I make a whole bunch of assumptions. So the general formula would basically tell us what we need to compute is some kind of path integral over all possible ways in which you can convert initial conditions to final conditions. And the rigorous argument you can make is basically spherical collapse is the most likely path, meaning essentially what you can do some kind of saddle point approximation, and a spherical collapse is indeed the saddle point. So now you're absolutely right, there are corrections to this, and actually part of this correction is included here because I didn't talk about this in a lot of detail. But it turns out that if you actually wanted to predict the nonlinear variance from spherical collapse, this wouldn't be accurate enough. So in some sense, part of this non-spherical contribution is already included here by saying, okay, if you need the nonlinear variance, you need to predict this from something that's not spherical collapse. So some part of this kind of non-spherical contribution is in there, but in principle, you're correct. You would need to include those higher order terms. And people have done this, and I think they called it extended perturbation theory. Essentially, those are the leading order corrections. And then you include higher order terms that are like sigma to the 4. And essentially, the sad message is if you look at the right scales, they're always suppressed. So I think for the tails, they matter a lot. I think in practice, if we stay close to the peak that is actually accessible in observations, I think it will be hard to actually see that.
How about this the delta L function? Because that's also modified in like ellipsoidal collapse. Do you
mean the linear variance here, or?
The delta L, the numerator? Yeah.
Yes, so in principle it would be modified, but essentially I think it's the way we construct the statistics, right? So essentially by choosing spheres, I know that if I average the profile of all of spheres, I will get something that's spherical just by statistical isotropy. So it's not relevant that in every single region I would actually have an ellipsoidal contribution. This kind of averages out by the kind of choice of statistics we make here.
Right, but the function you get from a spherical collapse is not the same as probably the true function, because probably the collapse is, I think, generally thought to be slowed down by ellipsoidal effects. So this functional dependence of delta L over rho on rho would probably be different for a smaller regions compared to, compared to what you get from a spherical collapse.
Yeah, in some sense, you could basically think about a way of modifying spherical collapse in a density dependent way, right? Of saying, for example, densities that are very far from the mean are more affected by this kind of tidal effects there. So yeah, in principle, you would have to include it. I think in practice, it turns out to actually work rather well in this way, which is the reason why we didn't set out to calculate this stuff. But yeah, you're right.
Okay, cool. Very exciting, thanks. Actually, I had another question. So when you said you did the same thing for a projection in weak lensing, so how do you do it exactly? Because then you don't have a spheres anymore. You have like a cylinder.
You're absolutely right. I actually just rushed over this. So essentially what you do here, so let me maybe go to this plot. So the key idea is you build up your whole cone out of lots of disks. And now for every single disk, you can basically pretend a disk is an infinitely long cylinder. So every disk individually will follow cylindrical collapse. And then you basically just have to integrate this up to compute your PDF.
So you assume cylindrical collapse.
Yes, so now you basically assume cylindrical collapse, and I didn't show it here, but the rough idea is very similar to spherical collapse. It's just a kind of different kind of power law here.
Interesting. Okay.
So yeah, the true difficulty is basically hidden in this integration here, right? Because you mix scales, for example, since basically the radius of your disks changes, right? So this mixes scales, and now you integrate from 0 redshift to your source redshift. So you basically see at the tip of the cone, you probe very nonlinear scales. So this is one reason why those kind of projected quantities are a bit difficult. But you could also try to remove the tip of the cone.
Yeah, I mean, the thing that's weird is, I mean, I guess in a cylindrical symmetry, you don't have Birkhoff's theorem. So I'm not sure this, is that an approximation, that function, that delta L, just a function of rho? Because I imagine it could also depend on the size of the region, or doesn't?
Yeah, I think in principle it could be. I think here the idea is if your cylinder is infinitely long, then it's like a 2D universe. So then you basically don't have collapse along the axis of the cylinder.
Okay. Yeah, I should think about it. So that's interesting. Thank you.
Thanks.
I have also a question. Did you think about how to do counting cell for galaxies, like the second option you had for real observations?
Yes, I did. Let me maybe, okay, I probably have one backup slide to just very roughly give the idea. I have tons of backup slides. Ah, there we go. That was the plot. So roughly speaking, the idea is very simple. If I can predict the PDF of the matter density, right? Now I can say all I need to do is to map to densities of tracers, right? In this case, it's not galaxies, it's subhalos. But roughly speaking, the idea is very simple. Well, you can do it, at least in a simulation, you can make a scatter plot, right? Relate all the matter densities you find to all the tracer densities. And now you can set out to basically parameterize this kind of joint PDF here. And once you parameterize this joint PDF, you can now predict the distribution for galaxy or any other tracer density. So this is the very brief answer. Essentially, what you need to parameterize here is some kind of mean bias relation and parameterize the kind of scatter or stochasticity here. And then you can map to galaxy counts and cells.
I see, and you don't know how much information you lose in this way. compared to the counting cell in matter.
So yeah, I think what's extremely interesting, I actually didn't get to mention this, but there is a so-called density split statistics out there that has been applied to the dark energy survey. And roughly speaking, the idea is you combine galaxies and weak lensing. So essentially you split you split lines of sight according to the galaxy density you find there. And then you look at the weak lensing tangential shear signal. So this is some kind of joint lensing and counts in cells. And in this case, they actually showed that, first of all, you can detect this non-Gaussianity there, even with dark energy survey year 1 error bars. And I think what's even more interesting, this kind of density split statistics are competitive with the standard 3 times 2 point analysis. So we can have a look at the 2 papers here where they basically show some contours. And the key thing is how many parameters would you need to actually parameterize the relation between matter and galaxies. So I think in their case, it's like a simple linear bias and some stochasticity term.
Okay, interesting, yeah. Are there any other questions?
I think I see one raised hand here.
Yeah, hi, it's Andre. Hi, Cora. Thank you for a very nice talk. So I have 2 questions, like one is maybe more interesting. So let's start. So we know like roughly that matter moves on like 10 megaparsec scales, just so spherical collapse doesn't care about this. And so, but still you smooth out over the scales that are roughly the same as like the size of how much matter moves. So did you ever make, or has anybody ever checked, like when you do reconstruction, what happens with these counts in cells? And yeah, like, because that should be like closer to linear field roughly, and it kind of undoes these motions, large scale motions. So I'm just wondering, like, is there some what happens when you do what you're doing but after reconstruction? That's the question.
Yeah, I think that the short answer is if you had a very good reconstruction, things would look very boring because then it should be Gaussian, right? So in some sense, you could test some aspect of your reconstruction by actually doing this kind of basically smoothing and then plotting the histogram and checking how Gaussian it is. Obviously, it doesn't give you all of the information because you could have 0 skewness, but still non-zero bispectra and stuff like this, right? So in some sense, I think we don't think about this because once you reconstruct it, you basically know it should be close to linear and then Gaussian. But we thought about it in a slightly different way, maybe inspired from this kind of log normal idea, right? So observing that the PDF is close to log normal, you could say, I can actually create kind of mock dark matter density field just by applying some kind of nonlinear transformation, right? So in some sense, what this whole formalism tells you is you could improve this kind of log normal assumption by something that depends on the spherical collapse. The crucial bit here is, however, it's not just a spherical collapse, but also there is some kind of dependence on cosmological parameters because you probe different scales in your initial conditions. So this is basically this kind of Eulerian to Lagrangian mapping. So in some sense, the way we actually predict this is by doing some kind of reconstruction, but not on the full field level, but on some kind of smoothed field level in which you also forget precise locations.
I see. Okay. And then, yeah, maybe then not, well, the other question was like, how do you compute these nonlinear sigma? And is it like degenerate at all with the linear one? Because I expect like on large scales, some part of that integral is very degenerate in cosmological parameters with a linear, with the sigma L, right?
Yeah, so what we do in practice is we essentially use halo fit to compute this nonlinear variance. So there's basically a cosmology dependence in here as well. But you can even find a very rough estimation of this nonlinear variance. So essentially you could assume your PDF is log normal, and then there's a relation between linear and nonlinear variances, some kind of log relationship. So this is a simple way to kind of estimate those effects.
Okay, so you kind of fix that halo fit thing, and then there is no like parameter that you marginalize over.
Yeah, exactly. So in this case, we basically just assumed halo fit for the nonlinear variance. And the key thing is we basically validated this against the simulation, right? And you can see that this works.
Okay, okay. Thank you.
I think roughly speaking, if you marginalized out the whole nonlinear variance, I think roughly speaking, you would probably lose information on sigma 8 because that is closest to just changing the variance.
Yeah, that was that was in the back of my mind when yeah. Thanks.
Actually, related to this question that Andre brought up, so if we do reconstruction and try to measure power spectrum from reconstruction, I mean, don't we get all the same information basically? I mean, have you done a comparison?
Well, it's an interesting question. In some sense, you could say, okay, if you believe that initial conditions were Gaussian, right? Then we essentially know all that nonlinear gravity can do is basically distribute all of this information included in the initial power spectrum in like higher order statistics. I think one exception is if you basically have non-trivial growth, right? So for example, dark energy, I think doesn't really follow this logic because then there's additional information in the growth of structure. So we haven't done any checks on this. Yeah, what can I say? Yeah, I think roughly speaking, the point is just one way of actually constraining growth is basically using the PDF. And in some sense, the PDF gives you some kind of mapping from initial to final densities, just in a very simple.
I understand. I'm saying that I mean, there is certainly information in the growth as well, but so there are kind of two ways to go about that. One is to do reconstruction, and the other is just to look at the statistics of what's the outcome, and which is, I mean, you're doing the second one, but it seems that they're essentially, I mean, of course, reconstruction is never perfect, and what you're doing is also is not perfect in the sense that you're not looking at all possible statistics, it's just some statistics you're looking at. So I guess my question is that if you want to compare the efficiency of these two approaches to this problem, I think it would be kind of interesting to do compare. I mean, how much do they do more or less the same thing, or is one more efficient, or is there something that one does and the other doesn't?
So I would say reconstruction should, well, overall give you better results, right? Because it operates on the field level. So obviously we only look at 1-point statistics, while reconstruction basically would also tell you how 2-point functions are mapped to like 3-point functions, 4-point functions, including kind of their angular dependence.
If it's done perfectly, but of course reconstruction is never perfect. So that's why it has limitations. Do you see what I'm saying?
Yeah, so I think that's a question for the people who do reconstruction. I think an interesting question would be if you basically try to estimate whether reconstruction works well on certain scales, and then you just say, okay, I can only reconstruct kind of the smoothed field. I think then this question would be easier to answer, because then you could measure statistics of the smoothed field, and the 1-point PDF would be one chunk of it. And you could basically measure kind of smooth 3-point correlations and just see how big they are.
Cool. I guess I'm proposing that you should collaborate with someone who does reconstruction and see who does better, basically. Thank you.
Thank you.
So if there are no other questions, thank you, Cora. And
thanks a lot. It was a lot of fun. Now I can actually see your faces again, which is great. Maybe I should have unshared my slides before.
Well, they are useful to answer to the questions, I guess. Okay, so let's see everyone next week for another talk.
Thank you. Take
Thank
care.
you.
Bye.